Welcome back to another video on Brownian motion. Today we are going to talk about the so-called law of the iterated logarithm. And that law is connected to both the strong law of large numbers and the central limit theorem. It's somehow in between. And what I mean by in between, I have a picture for you, which is on one of the first slides. Let's see. So let us talk about the law of the iterated logarithm. To start with, what all that means. Here's the picture that I wanted to present. So here I have two paths of Brownian motion. And the goal of this law is to find a curve, which will be this curve here, such that almost surely the Brownian path, well, it will touch on the curve, but it will not go beyond it very often and not stay, the maximum will not stay below it very often. In the sense that, here as I write it, xt divided by this curve here, so that's square root of 2t log t, the lim sup is going to be 1. So this here, the fraction of these two things is going to be 1. In this curve, yeah, you might believe it. In this curve, you might not believe it because it behaves differently. But, well, it has a lot of time and can go down and up and hit that curve again and again and again. So, well, so the square root of 2t log t might seem a bit funny. So let's see if we can say something about this without knowing the law of the iterated logarithm. So our goal is to find some function ht, which will be the square root of 2t log t, such that this here holds. So the lim sup is somewhere between 0 and infinity. It will be this lim sup here will be a constant because the tail sigma algebra of Brownian motion is trivial. But what is the ht here? For example, we could guess ht equals t. But, okay, xt divided by t goes to 0 because we can write xt as a sum of independent random variables with all mean 0. That means that he converges to the mean of the sum of what we have here. So expectation of x1, for example, is 0, so that must converge to 0. So ht equals t cannot be that function here. But with some experience, we say, well, what about square root of t? Because that also appears in the central limit theorem. But, well, this lim sup will be infinity. Why is that? Okay, assume xt divided by square root of t goes to some gamma, which is finite. Then we had to conclude that, well, the probability that xt divided by square root of t is bigger than 2 gamma. So 2 gamma here, so here gamma, here 2 gamma. That must be 0 because the lim sup is going to be gamma, so it almost never is above gamma. So, but for big T, xt divided by square root of t has an n0,1 distribution, and the probability that this is bigger than 2 gamma, well, that's something finite, so it can't converge to 0. So that lim sup must be infinity, which means that we know that the ht we're looking for is somewhere between square root of t and t. And I will show that it's square root of 2t log t. And it's called the iterated logarithm because you have the log here. So the law is iterated. First of all, some remarks. Well, the lim sup is 1, but the lim inf is -1. That's clear because the lim sup is the upper curve here, and the lim inf is what the Brownian motion does here with its infimum. So the infimum must be -1 by symmetry. Yeah, actually, what I did not say, well, but that's in the law here. I have a lim sup t goes to infinity, but I also have a lim sup for t goes to 0. So how does Brownian motion come out of 0 here, such that I have also a 1 here? But actually, we already saw that we can translate results on Brownian motion for t goes to infinity to results on Brownian motion going t to 0. The property that we already know. Let me start with this, which is exactly what I want to show here. And t goes to 0. For this equality, I exchange t by 1 over t, which results in simply this. And now I multiply the numerator and the denominator by t. I have a tx prime 1 over t on the numerator, and on the denominator, the 1 over t under the square root goes to a t. So I have this thing here. And for t goes to infinity, the right-hand side, the lim sup of the right-hand side converted to 1 because this here is a Brownian motion. But t goes to infinity on the right-hand side, because we use t goes to 1 over t here, means the t goes to 0 on the left-hand side. And that's exactly what I claim here, that this here is 1. So we can show that this lim sup is 1 from the proof that this lim sup here is 1. Okay, all what remains is showing the lim sup for t goes to infinity. And we're going to use this by, some notation here. ht is squared of 2t log t, okay. And I'm going to write that a and b are similar if their quotient converges to 1. So let us start with a very important estimate on the normal distribution. So x is normally distributed with variance 1. So then the probability that x is bigger than x is at most 1 over x phi of x, where phi is the density of x. And so it's an upper bound, and a lower bound is x divided by 1 plus x squared phi of x. And I could then also write what I'm going to do. That's approximately for x goes to infinity. Well, x divided by 1 plus x squared as x goes to infinity is about 1 over x. So I have a lower bound and an upper bound, which are approximately for x goes to infinity the same. And I can write this thing here. So that's about the same, because the quotient converges to 1. So let me show these two properties. And that's actually not that hard. I need two things. Phi prime of x, where phi, by the way, is the density of x. So phi prime of x, okay, that's 1 over the square root of 2 pi times e to the minus y squared over 2. And when I make a prime, so if I take the derivative, then I get the same function and a minus x in front of it by the derivative of the exponential. And using this, I can write phi of x. Well, that's of course the integral from x to infinity of, well, minus phi prime of y dy. But phi prime we just computed, y phi of y. And that y here in the integral is larger than x. So that means I can bound it from above. From below. phi of y dy, that's bigger or equal than x times the integral phi of y dy. And the integral now is the probability that x is bigger than x. And I bring the x to the other side, and I have the first estimate. And for the second estimate, there's a similar trick. And the trick is, if I have phi of y divided by y and take the derivative, well, I have a y squared in the denominator. I have a y times phi prime, which is minus phi. So wait. Yeah, minus y squared, because I have one y from the denominator and one from the derivative of phi, minus the numerator, which is phi, times the derivative of y, which is 1. So I have minus 1 here times phi of y, such that I can write again phi of x divided by x equals the integral of x go to infinity minus the derivative of this, and minus the derivative of this here is y squared plus 1 divided by y squared phi of y dy. And now looking at this function here, where is this largest? That's largest for y the smallest, such that I can have an upper bound by using 1 plus x squared divided by x squared times the integral over phi of y from x to infinity. Okay, we know what happens there. So that's the probability that the x is bigger than x. And now bring the x squared to here, 1 plus x squared to here, I exactly get the bound that I would like. Okay, that's this proof. And what we will also need is the following. And here, please recall what we had last time. We had that the supremum of Brownian motion is distributed as the absolute value, and we know the density. And the density is 2 times the density of Brownian motion itself on the positive side. So this here is the same as xt bigger than x squared of t. Here use the other theorem. And now for x goes to infinity, x goes to infinity here, well, xt divided by square root of 2 has a normal distribution with variance 1. So I can use the result here. And I can use, in particular, this result here. That's about 2 over x phi of x. And we are going to use this. So now let's come to the proof of the law of the iterated logarithm. I need to prove two things. I need to prove an upper bound here, which means the lim sup is at most 1, or is at most 1 plus epsilon for all epsilon. And I will need a lower bound, which means it's bigger than 1 minus epsilon. And both the upper and the lower bound are connected to the Borel-Cantelli lemma, which means I need to define some events and show if their probabilities are summable or not. So first of all, I will have an R and I will have an N, and n is going to infinity, and r is bigger than 1 here. So what is h of r to the n minus 1? H was the function which maps t to the square root of 2t log log t. And when t is this thing here, and n is large and r is finite, it's important to note that log log r to the power n minus 1, well, that's of course log n minus 1 log r, which is log n minus 1 plus log r. But log r is much smaller than log n, in the sense that this here is about log n. Okay, the minus 1 also doesn't play a role, so I can use this thing here. And I did that, so the square root of log r to the power n minus 1 goes to the log n here, as we have here. Okay, I also have a square root of r to the n minus 1, and that's square root of r to the n divided by square root of r, like this. Why did I do this? I did this because now I can write for some positive c, which will here be such that this here will hold. I have this supremum here. And remember, again, using our result from the reflection principle, the distribution of this thing here is as the absolute values. So I have the equality here, where x at the time r to the power of n is bigger than what I had here. But what I had here is about the same as this, as we just shown. So I have this. And, well, n is large, which means this here is a large thing. And we had the estimate, like here. That's of the same form. I only have to be careful. Here's a t, and here's the square root of t. But that's exactly how I wrote this. Here I have an r to the power of n, and I have a square root of this thing here. And we know from this here that that's about 2 over x. So x is what stands in front of the square root of t times phi of x. So 2 divided by c divided by, well, this thing here. I have the r divided by log n. I have a 2 from here, and I have a 2 from here, which means that I have this thing here, times phi of what stands in front of this thing here. So this is this. But remember, let me write that here, phi of x equals 1 over square root of 2 pi e to the minus x squared over 2. And if x is large, well, I can also bound this. I have 1 over square root of 2 pi. So 2 goes away and I have a pi in the denominator. And phi evaluated as this thing here. So let me say, well, if I would like to get rid of this c here, I can write a c square in the square root. But then I can also ignore that 1 here and write a c square instead. That's the same by laws for the logarithm. Yes, like this. And when I square this thing here, I have 2 log n to the power c squared over r. If I take divided by 2, I have log n to the c squared divided by r. And a minus also from the minus here. But e and log, that just goes away. and it stays n to the power c squared over r. And because I had a minus here, I'm having this in the denominator, which means I have this thing here. And if now c squared is bigger than r, I have n to the power of something bigger than 1, which means that this thing here, in n, is summable. So if that's summable, I know only finitely many events of this form here occur. But if lim sup of xt divided by ht is bigger than or equal than c, it must be the case that, well, the supreme exceeds c at ch at time r to the n minus 1 infinitely often. And that probability here must be 0, as we just computed using the Borel-Cantelli lemma. And that was it for the upper bound. And there we used the Borel-Cantelli lemma for the version where we did not need independence. But for the lower bound, we need something independent. So the estimate is a bit more involved. And we have these events here. And we're going to show that these events here, well, there's something not summable, which means only finitely many of these events here occur. And what are these events? Well, the events are that between times r to the power n minus 1 and r to the power of n, the increment is larger than c times the function that we want to have, evaluated at the time difference here. Okay, we can compute nice things. So the probability of an, we can compute this because, well, that's the distribution, which means the distribution divided by the square root of the variance has an n01 distribution. So P of an, okay, the numerators are what we really have, and I divide this by the square root here, because then I know what the left-hand side has for distribution, so that's x1. And for the right-hand side, so h evaluated at this thing here, is square root of 2 log, what is written here? 2t log t, and the t goes away with that square root here. So it remains 2 log of this thing here. And r is bigger than 1 and c is less than 1. Okay, that's also important. Yeah, but again, we will need here our basic estimate for the normal distribution. Yeah, 1 over this thing times phi evaluated as this thing here. 1 over this thing, 1 over c2 log thing. 1 over 2 pi comes from the phi, and e to the minus, well, this thing squared divided by 2 is e to the minus c square log here. And now if n is going to be large, we already had that this thing here is log n. I have written this here. And for the other thing, well, okay, we know that this here is about log n. And so we have log n to the power of c square. And with a minus here, I get this here, 1 divided by n to the power of c square. But now c is less than 1, which means that this here is not summable. And that means infinitely many of these ans here occur. So infinitely many en occur, which means exactly this thing here. So x at time r to the power of n. So the increment is larger than this infinitely often. Now we're almost done. We only need to put everything together. So, okay, I want to know something about this thing here, lim sub xt divided by ht. But that's rather the same as evaluating x to the power rn divided by h at r to the power of n. But I don't know anything about this because I only know things about the increment. But I can use, well, first of all, h at r to the power of n is about the same as h at r to the power of n minus r to the power of n minus 1 if r is large. That's one thing. And I can use minus x evaluated at r to the n minus 1 plus x evaluated at r to the n minus 1. And for the plus bit, I have to bound it from below. And I can actually use this, the upper bound for this, because I know that x at r to the n minus 1 is bigger than minus 2 times h at this time point for almost all n. And I'm using this thing here and divided by r to the power of n. Well, I have this thing here, which is this, which I use here. So minus 2 to 2 divided by square root of r. So I have this thing here. This lim sup here is bigger than c because we know this occurs infinitely often. I also write down the minus 2 divided by square root of r. Now let r go to infinity and c go to 1, which I can do here, which means that this lim sup here is bigger or equal than 1, which is exactly the lower bound for the law of the iterated logarithm. Okay, now we're done with this law. And next time we're going to know about a so-called functional central limit theorem, also for Brownian motion. See you then.